The components of a given vector will be different for different choices of coordinate axis, but the actual magnitude and direction of the vector does not change with the change in the direction of the coordinate axis. The choice of coordinate axis is always arbitrary. The point here is that we have a great freedom in choosing a coordinate system, because the relations among vectors do not depend on the location of the origin, or on the orientation of the axis. Can you try yourself to see if the above statements are valid or not?
Okay. How should I approach this problem?
You can try this in different ways. For example, take any two vectors in a coordinate system, add them to obtain the resultant vector. Then rotate the coordinate system and see how the results change.
This is interesting. Let me do that. Let me take a right-handed coordinate system wherein the x and y axes are parallel to the edges of the book. In this system, I will consider a vector, a bar, having magnitude of 3 units, and which makes an angle of 45 degrees with positive x-axis. And another vector, b bar, having a magnitude of 3 units, and which makes an angle of 135 degrees with positive x-axis. Therefore, vector a bar can be represented as a bar is equal to 3 cos 45 times I hat plus 3 sin 45 times j hat. Similarly, vector b bar can be represented as b bar is equal to minus 3 cos 45 times I hat plus 3 sin 45 times j hat. If the vector sum of a bar and b bar is r bar, then r bar is equal to a bar plus b bar, which is equal to 3 cos 45 times I hat plus 3 sin 45 times j hat plus minus 3 cos 45 times I hat plus 3 sin 45 times j hat, which is equal to 6 sin 45 times j hat. Therefore, magnitude of the resultant vector is equal to 6 divided by root 2, which is equal to 3 root 2. The resultant vector is along the positive y-axis. Therefore, the vector r bar makes an angle of 90 degrees with positive x-axis. I will now rotate the x and y-axis together in counterclockwise direction for 45 degrees about the origin. I will then see how the vectors and their vector sum would be in this new coordinate system. Let me name the new x and y axis, obtained after rotating x and y axis in counterclockwise direction for 45 degrees as x prime and y prime, respectively. Now the vectors a bar and b bar will be along x prime and y prime axis, respectively. Therefore, in the new coordinate system, vector A bar is along x prime axis, and vector B bar is along y prime axis. I will now calculate the vector sum of A bar and B bar in the new coordinate system. Since vector A bar is along x prime axis, vector A bar is equal to 3 times I hat. Similarly, since vector B bar is along y prime axis, vector B bar is equal to 3 times j hat. I will call the vector sum of the two vectors, A bar and B bar, in the new coordinate system as r prime bar, which implies r prime bar is equal to A bar plus B bar, which is equal to 3 times I hat plus 3 times j hat. Therefore, magnitude of the vector r prime bar is equal to square root of magnitude of vector A bar whole square plus magnitude of vector B bar whole square, which is equal to square root of 3 square plus 3 square, which is equal to square root of 2 and 2, 3 square, which is equal to 3 times square root of 2. And r prime bar makes an angle of theta with x prime axis, where theta is equal to tan inverse 3 divided by 3, which is equal to 45 degrees. Now, if I compare the resultant vector obtained by adding A bar and B bar in both the coordinate systems, I see that the magnitude of the resultant vector is the same, which is equal to 3 root 2. Coming to the direction of the resultant vector, I see that in the first coordinate system, the resultant vector makes an angle of 90 degrees with the positive x-axis. And in the second coordinate system, the resultant vector makes an angle of 45 degrees with the positive x prime axis. But I rotated xy axis by 45 degrees in counterclockwise direction to obtain x prime, y prime axis, which means that the resultant vector r prime bar is at an angle of 90 degrees with x-axis when compared to the first coordinate system, which is the same angle the vector r bar made with positive x-axis. From the law of equality of vectors, two vectors are equal if the magnitude and the direction of both the vectors are equal. Since the magnitude and the direction of the vectors r bar and r prime bar are the same, I can say that r bar is equal to r prime bar. Therefore, the direction of the vectors does not depend on the orientation of the coordinate axis chosen.
Good. That's correct. Another way to arrive at the same conclusion, without using math, is remove the coordinate axis and calculate the direction of resultant vector. Say, using parallelogram method. You will see that the resultant vector, in this case, bisects the angle between the vectors a bar and b bar. Therefore, with the coordinate axis 2, the direction of resultant vector should not change, irrespective of the orientation of the coordinate axis. Remember that we introduced coordinate axis to simplify the process of doing vector algebra. It should and would never alter the result of vector algebra, only simplify the process of doing it. Which is then the right pair of coordinate axis to choose?
They are all equally valid, because each pair of coordinate axes just gives us a different way of describing the same vector. All produce the same magnitude and direction for the given vector.
That's correct. Using this concept, we can often reduce the work involved in solving a problem by wisely choosing the coordinate axis. In the same example you took, we can directly start by taking the coordinate axis to be aligning with one of the vectors, so that the vectors would have only one component, which would reduce the work involved.